Greetings from Hunter College. My name is Isaac Berry, and today we're going to be doing lecture number 16 of real analysis, and we're going to be proving the Heine-Borel theorem part 1. Now, we have 3 parts, as we remembered before. 1, we have that a set S is closed and bounded. 2, a set S is sequentially compact. And 3, a set S is covering compact or just compact. Alright. So, today we're going to be proving the easiest one of these, which is going to be proving that 1 is equivalent to 2. Or in other words, proving that a set S is, or that 1 implies to, set S is closed and bounded if it is, or is it 2 implies 1 technically? Yeah. If it is sequentially compact. Oops. So, we know sequentially compact means that every sequence whose elements are in S, or let me write it more formally. For all sequences, or rather, for all AN, such that AN is in our set for all natural N. So for all of these sequences, S is closed and bounded, or rather S is sequentially compact. Oops. If it's sequentially compact, if for all convergent subsequences i.e. subsequences for which a limit exists, and there must exist at least one by the Bolzano-Weierstrass theorem as long as the set is bounded. If for all convergent subsequences a sub n sub k if for all convergent subsequences a sub n sub k, the limit L is in the set as well. So prove our set is closed and bounded. So let's think about it. What does it mean to be closed? Well, it means to contain all limit points. Hopefully you know what limit points are. So, then that means that if we have a sequence, for example, we could have 2 possibilities. Either our sequence AN converges, or it does not. In which case A sub n sub k will converge for some n sub k. So in the case A sub n converges, it's very easy to see why. A sub n converges It's very easy to see why if a sub n converges here, the limit L of all of the sequences is going to also be an S. Well, let's think about it. What does it mean to be closed? To contain all limit points. And so, one of the limit points is going to be the limit of an. So let's assume that an approaches L. So then, that would imply, so have an minus 1, some point of no return after which it gets sucked in, plus 1, and plus 2. So, this is the big guy itself, L. So then, L would have to be a limit point. And since S contains all limit points, since it's closed, L must be in S. And here's the thing. Since A of n converges, all of its subsequences converge, and to the same number as well. So, since L is in S, this means that all of the convergent subsequences here converge to something that is in the set. Alright, but what about in the case A sub n doesn't converge? Well, then A sub n doesn't have any limit L, doesn't exist. So then, we have subsequences which may approach different limits. For example, 1, 0, 1, 0, 1, 0 has no limit, but we have several subsequences, like, for example, 1, 1, 1, 1, 1, and 0, 0, 0, 0, 0, which each have their own limit. This one goes to 1, this one goes to 0. Same thing with other more complicated ones. We may have two subsequences that have different limits. So, what do we do in this situation? Well, we need to still be reminded, n sub k has to be in the natural numbers, right? A sub n sub k is just another sequence. It approaches another limit point, L. And let's say we could have a different convergent sequence, A sub n sub k prime. Let's say there are only two convergent subsequences. Of course, there could be more, but then this just applies ad infinitum. I don't know how to say it. Ad infinitum is what I'm going to go with. So, A sub n sub k prime, for example, goes to L prime. So then, what does this mean? Well, both L and L prime are limit points, because they're limits of convergent sequences in our set. So that means that L and L must therefore be in S because S is closed. Now, you may be realizing that we forgot one thing. Yeah, that's right. We effortlessly proved that all of these were closed, but what about bounded? Well, still pretty simple for the A sub n converges case. So, when A sub n converges, we can see that if we just take the epsilon neighborhood, or here's what we can do. We can take the maximum of A sub 1, A sub 2, A sub 3, A sub 4, ... And then all we can do is take L plus epsilon. The maximum of this whole thing, and if you really wanted to, you could also tack on an. The maximum of this thing has to be the maximum of the entire sequence, since we know that after some point, for all n which is greater than or equal to n, L minus epsilon is below an, and L plus epsilon is above, which means we have that upper bound and lower bound. We have all but finitely many, which are duking it out for first place, since we have only finitely many that are duking it out for first place, and we can thus take the maximum of them. There are only n plus 1 entries in this entire list, n is finite, so it works out at the end of the day. So this can be some number. You can call it m for max. Doesn't work out for the minimum though. So then, it's pretty easy to show that m is the maximum. And you can do the same exact thing with the minimum if you just take all of these and then L minus epsilon. So there's a maximum and there's an existing minimum. Pretty simple, right? Now, what about the case in which a sub n doesn't converge? Well, remember, a sub n sub k, a sub n sub k prime, they're their own sequences. They're literally just this case, but repeated with a few more layers. So, that means that in this case, we've got something bounded as well. So, certifiable that this half is bounded when an doesn't converge, and this half is bounded when an does converge. And, how do we know that there isn't just another sequence which spirals off into infinity, even though this one stays contained? Because this has to be true for every single sequence. Every single sequence has to fall within these bounds. Same thing over here. Every single sequence has to fall within these bounds. So now we can show the set S is closed and bounded if it is sequentially compact. The parts only get harder from here, so this is the easiest one. Then we'll be moving on to showing that.
Part 2, right?
Yep. We'll be moving on to part 2 next time.